Hello again, welcome back to College Algebra, and today we're in section 3.3 and we're going to be talking about zeros of polynomial functions. So we're going to pick up a few theorems in this section. The first theorem I'll show you is called the factor theorem, and then we'll talk about the rational zeros theorem, and we'll talk about how to determine the number of zeros that a polynomial has. We'll take a look at what's called the conjugate zeros theorem, and then we will look at Descartes' rule of signs. So let's get started. The first theorem we're going to look at is called the factor theorem, and it just says this. It says for any polynomial function f of x, if you have a number k and f of k equals 0, then that means that x minus k is a factor of the polynomial. And it works the other way around too. If you know that x minus k is a factor of the polynomial, then that automatically means that f of k equals 0. And remember, we learned in the last section that if f of k equals 0, that means k is a 0 of the function. Now, this is actually something that you already knew. It may sound strange when we talk about it in terms of polynomials, but you actually already had a feel for something like this. So, for example, if I ask you, is 3 a factor of 116? You might say, well, gee, I don't know. Let me divide and find out. And when you do 3 divided into 116, you find out that there is a remainder. And when you see that remainder, you say, well, then no, 3 is not a factor of 116 because it didn't go into 116 evenly. And that's what we're doing here. If f of k equals 0, that means that when you divide by x minus k, the remainder is 0. And if the remainder is 0, that means that x minus k went in evenly, and therefore x minus k is a factor of what you were dividing into. So really, this is just restating something that we already knew from common sense, just working with regular numbers. Okay, so here is example 1, and we are going to determine whether x minus 1 is a factor of this polynomial. Okay, if x minus 1 is a factor of this polynomial, then when we divide by x minus 1, there will be no remainder. So how do we divide by x minus 1? Well, we'll use synthetic division, and we'll put a 1 in the box, and then we'll copy all of our coefficients here. So notice that I don't have an x to the third term, so I had to put a 0 to hold that place for the x to the third term. So I have 2x to the fourth, 0x to the third, 3x squared minus 5x, and plus 7, and we're dividing by x minus 1, so we have 1 in the box. So now pull down the 2, then multiply 1 times 2 is 2, then add, and then multiply 1 times 2 and put that here, and then add, and then multiply 1 times 5 and put that here, and then add, and 1 times 0 is 0, and then add. And because this is not 0, that means f of 1 is not equal to 0, and that means x minus 1 is not a factor. See, when we divided by x minus 1, we got a remainder. Therefore, x minus 1 did not go in evenly, therefore it's not a factor. Now let's find out whether x minus 1 is a factor of this polynomial. So again, we'll put the 1 in the box, and we'll copy all of our coefficients here. And let's go through the synthetic division. So pull down the 3, then multiply, add, multiply 1 times 1 and add, multiply 1 times 2 and add, multiply 1 times negative 6 and add, multiply 1 times negative 1 and add. And this time, when we divided by x minus 1, we got a remainder of 0. And that means that f of 1 is 0, and that means that x minus 1 is a factor of our polynomial. Okay, now we're going to move on to example 2, and this one says factor this function into linear factors given that negative 3 is a 0 of f. Okay, what are they telling us here by telling us that negative 3 is a 0 of f? Well, if negative 3 is a zero of f, we know that means that f of negative 3 equals 0. That's what it means for something to be a 0. Remember? It means if you plug it in, it equals 0. Now the factor theorem tells us that if f of negative 3 equals 0, that means that x minus negative 3 is a factor. And we would never write this as x minus negative 3. We would always write this as x plus 3. So if negative 3 is a 0, that means x plus 3 is a factor. In other words, when we divide by x plus 3, the remainder you see is going to be 0. Now if x plus 3 is a factor, that means x plus 3 times something else has to equal this polynomial. And the way to find out what the something else is to do the synthetic division, dividing by x plus 3. So we'll have negative 3 in the box. Remember, if we know that, for example, 30 divided by 5 equals 6, then we can turn that around and say 6 times 5 is 30. So if we know that f of x divided by x plus 3 is some other polynomial, we can turn that around and say that other polynomial times x plus 3 equals this big polynomial. So let's go ahead and do our synthetic division. I have my x to the third coefficient, x squared, then x, and then constant. And I have negative 3 in the box. Remember, if x plus 3 is a factor, that means that we put negative 3 in the box, and we're going to have to get a remainder of 0 here, or we did something wrong, because we know that negative 3 is a 0. So let's do our synthetic division. We pull down, multiply, add, multiply, add, multiply, add. There is the 0 that we were expecting, and these are the coefficients of the other factor. So now we have split f of x into two factors. We knew that x plus 3 was a factor. The other factor comes from the quotient. So 6x squared plus x minus 1. And now notice that the instructions said factor into linear factors. So there's more factoring that we have to do, but now we've whittled that function down to a quadratic expression, and we can do the factoring on our own from here. So we know x plus 3 is a factor, don't lose that, but we'll now factor this trinomial into two binomials. Okay, 6x squared is going to break down into 3x times 2x, and the signs need to be different, and last times last is 1, so I pretty much have to have 1's here. And now let's see if we get outer plus inner to make that middle term that we need. Outer times outer is 3x, inner times inner is minus 2x, then 3x minus 2x is positive 1x, and that's what we needed. So here are our linear factors for f of x. Now here is a practice problem, and if you understood the last example, you should be able to do this practice problem on your own. So I would encourage you to stop the video and try this one yourself. And now I'm going to work through it with you. So here we have f of x equals 2x to the third minus 3x squared minus 17x plus 30. And we need to factor this into linear factors given that 2 is a 0 of our function. Now since 2 is a 0 of our function, that tells us automatically that x minus 2 is a factor. So we know that when we do the synthetic division with 2 in the box, we're going to get a remainder of 0 because it tells us that 2 is a 0, but that also means that x minus 2 is a factor. So let's go ahead and put down our coefficients. So we have our x to the third coefficient here, then x squared coefficient, then the x coefficient, then the constant. So everything's represented. And then, of course, we know 2 is a 0, so 2 goes in the box. And now we pull down the first number, multiply 2 times 2, then add, multiply 2 times 1, and then add, multiply 2 times negative 15, and then add. And so now we have broken f into two factors. X minus 2 is one of the factors, and the other factor is 2x squared plus x minus 15. So again, remember that the instructions said to factor x into linear factors, and this is a quadratic factor, so this now needs to be factored. into two linear factors. So don't lose your x minus 2, but we'll break this trinomial down into two binomials. So 2x squared is going to break down into 2x times 1x. Then this last term is negative, so that tells me the signs here need to be different. And I'm just going to put plus here and minus here. And then last times last is 15. So that makes me think maybe 3 times 5. So I'll put the 5 here and the 3 here. And now I need to make sure that I've got it all arranged right. So I need to add up outer plus inner and see if I'm going to get the middle term that I need. So outer times outer is going to be minus 6x, because minus 3 times 2x is minus 6x. And then inner times inner is going to be positive 5x. Now negative 6x plus 5x is going to add up to negative 1x. But we needed a middle term that was positive 1x. So now I know that I need to switch these signs. And there we go. Now when you multiply 2x minus 5 times x plus 3, you would get this trinomial back. So here are our three linear factors, and that is what the question was asking us for. So that one's finished. Now let's talk about the rational zeros theorem. Notice that on the last two examples that we did, we would not have been able to start the problem if they had not given us the first zero to work on. So now we're going to find out how we can find our own zeros when one is not given to us. So suppose f is a polynomial function with integer coefficients, and suppose that p over q is a rational number written in lowest terms. So p over q is a fraction and it can't be reduced. And so what we can say is that if p over q is a zero of f, then that means the p number is a factor of the constant term in the original function, and the q number is a factor of the coefficient for the leading term, or in other words, the first term in the polynomial. So one more time. If p over q is a zero, then that means that the p number, which is the top number, has to be a factor of the constant term, and the q number, which is the bottom number, has to be a factor of the first term. So just to give you a little better handle on what's going on here, let's look at this polynomial. Here we have 6x to the third plus 35x squared plus 21x minus 20. And I've already factored this for us. This polynomial factors into 3x plus 4 times 2x minus 1 times x plus 5. Now notice that this is not a problem to work. There's no question here. I'm just trying to show you something about the rational zero theorem so you'll understand it a little better. Since we have the factors for this polynomial, we can find the zeros for this polynomial by setting each factor equal to 0. So whatever x value makes this first parentheses equal 0 is going to be a 0 of the polynomial, because think about it, if this parentheses equals 0, then 0 times whatever is going to be 0. So whatever makes each of these parentheses equal 0 is a 0 of the whole polynomial. So what if 3x plus 4 equals 0? Well, that would mean that x would be negative 4/3. So negative 4/3 is a 0 of this polynomial. And we can do the same thing with the second factor. If 2x minus 1 equals 0, that means that x equals 1/2. So 1/2 is a 0. And then if x plus 5 equals 0, then x equals negative 5. So that's also a 0. So now here are our three zeros for this polynomial. Now notice that for each one of these, the top number, which we call the p number, is there because it was a constant in the factor. And these numbers are in the factor because they are factors of this constant in our polynomial. Notice 5 and 1 and 4 are all factors of 20. So that's why they ended up where they did. So the top number of every zero has to be a factor of the constant term in the polynomial. And then the bottom numbers that you see here, the 3, the 2, and the 1, are all there because they were coefficients of the x term in each factor, and they're coefficients of the x terms because they're all factors of 6. So the bottom numbers are always going to have to be factors of the leading term. Now, what good does the rational zero theorem do us? Well, it just helps us build a list of possible rational zeros. So, for example, if we were asked to find the zeros of this polynomial, but we didn't have a zero to start with and we didn't know the factors, then what we could do is generate a list of potential zeros by listing all the factors of the constant and all the factors of the leading coefficient. And we know that any number that is a zero is going to have one of these factors as its top number, and it's going to have one of these factors as its bottom number, and that way we just get a potential list to work from. So let's take a look at this polynomial. So here we have f of x equals 6x to the fourth plus 7x to the third minus 12x squared minus 3x plus 2. And we're not given any of the zeros, but notice that part A says list all the possible rational zeros. So to get a list of possible rational zeros, what we do is we make a p list and a q list, and then the p over q combinations are the possible rational zeros. So now the p numbers, remember, are the factors of the constant. So since the constant is 2, the p numbers are going to be the factors of 2, and that's just 1 and 2. And the q numbers are the factors of the leading coefficient. So the leading coefficient is 6, and the factors of 6 are 1, 2, 3, and 6. And now our possible rational zeros are all the p over q combinations we can make. And we'll have to consider both the positive and the negative of each of those p over q combinations. So to make our list of p over q combinations, first let's take this 1 and put it over each of these q numbers. So that's going to give us 1 over 1, 1 over 2, 1 over 3, and 1 over 6. And then let's take the 2 and put it over each of the q numbers, and that's going to give us 2 over 1, 2 over 2, 2 over 3, and 2 over 6. Now, there's no sense in listing any number twice, so numbers that are duplicates can be ruled out. So as I go through here, I'm going to simplify each fraction, and if it's already in the list, I'm just going to omit any duplicates. And I'm going to put a plus minus in front of each possible rational zero. So 1 over 1 simplifies to 1. So positive 1 and negative 1 are both potential rational zeros. Now, while I'm here, notice that 2 over 2 would also simplify to 1, so I'm just going to go ahead and cross both of those out. They are both represented by this plus or minus 1 here. Then we have 1/2. So that can't be simplified, and there are no duplicates, so we'll put 1/2 in our list, and we need to mention that it's positive or negative 1/2. And then we have 1/3. Now notice that 2 over 6 would also simplify to 1/3, so we're knocking out 2 of these here, and so we're going to list plus and minus 1/3 and cross both of those out. And then we have 1/6, so plus or minus 1/6, and then we have 2, so plus or minus 2, and plus or minus 2/3. And here is our list of possible rational zeros. So I want you to think for just a second about what we've got here. The reason we say these are possible rational zeros is because not every number in this list is going to be a zero. Notice I could only have 4 zeros maximum because this is a 4th degree function. So for sure they can't all be zeros, but anything that is a rational zero is going to be in this list. So is it possible for 1/7 to be a zero of this function? No, it's not possible for 1/7 to be a zero of this function, because if it were, it would show up in this list. Now, why do we have to specify that these are possible rational zeros? Well, all of the zeros that can be written in fraction form are here, but there might be zeros that are not here, such as any zeros that are complex or imaginary, and any zeros that contain irrational numbers, like numbers that contain radicals, which might come up from using the quadratic formula. So the possible rational zero theorem can't help us find those things, but it can allow us to make a list of any rational, or in other words fractional numbers that might possibly be zeros of our original function. So in part A of this example, we made a list of possible rational zeros. Now in part B, they're going to ask us to find all the rational zeros and factor f of x into linear factors. So let's remember what we did in part A. In part A, we made this P over Q list. These P over Q numbers are the possible rational zeros. Now some of these numbers are actually zeros and some of them are not. So what we'll have to do is just pick a number from the list, do synthetic division with it, see if we get a remainder or not. And if we do get a remainder, then we know that number is not a zero. And if we don't get a remainder, then we know that that number is a zero. So it's a trial and error process. So what I'm going to do is copy down my coefficients from the polynomial. So note that we have x to the fourth, x to the third, x to the second, x to the first, and then the constant. Now the first number I'm going to test is the positive 1 from my list. And let me just tell you the game plan here. I'm going to test positive 1, and if it works, then I'll say, great, I found a 0. And if it doesn't work, then I'll know that positive 1 is not a 0, and I'll try negative 1. And if neither one of those numbers works, you might think that the next thing I would do would be to try the plus and minus 1/2, but actually, because 1/2 is a fraction, it makes the synthetic division process just a little more complicated, of course. So instead of using the fractions, first I'm going to go through every possible whole number that I have. So first I'll work with plus and minus 1 and plus and minus 2, and I wouldn't work with a fraction unless I had run out of whole numbers. So let's run through the synthetic division using positive 1 as our possible rational 0. And so we pull down the 6, then multiply, add, multiply, add, multiply, add, multiply, add. And guess what? We just found out that 1 is a 0 of this function. So that tells us for sure that x minus 1 is a factor. And now what we have is we've broken our function down into two factors, the x minus 1 that we divided by and the quotient from that division process. So f of x is now x minus 1 times 6x to the third plus 13x squared plus x minus 2. If you took the time to multiply these two factors back together, it would go back to looking like this. All we've done is factor out an x minus 1. And you see, this is what's so nice about the synthetic division process and the factor theorem, is it lets us factor expressions that we could not have factored any other way. You think about it. If I had asked you to factor this fourth degree expression, you would have been totally stuck, and I would have been totally stuck. But using the factor theorem and the rational zero theorem, we were able to break this big fourth degree function down into a linear factor times a third degree expression. So this is good. We're making progress. Now, if this were second degree, in other words, if this were quadratic, we could factor on our own from here. But notice that it's still third degree. So now what I'm going to do is I'm going to use the same P over Q list, and I'm just going to pick another whole number from the list and see if I can find a 0 of this function now. So now I'm going to go to a new slide, so I'll just have a little more room to work, and let me catch you up with where we are. So remember, we had a list of possible rational zeros. Here they all are. And we already had done the synthetic division to factor this big fourth degree expression into a linear factor times a third degree expression. Now I'm still going to be pulling numbers from this list of possible rational zeros, but now I only have to find one that goes into this third degree expression. So that makes it a little easier. And since we already used the positive 1, this time I'll use the negative 1. And let's just go through the synthetic division here. So we'll pull down the 6, and then we'll multiply, add, multiply, add, multiply, add. And you can see that f of negative 1 is equal to 4. That means negative 1 is not a 0, so we'll just discard this negative 1. And now let's try it with positive 2 in the box. So going through the synthetic division process again, pull down, multiply, add, multiply, add, multiply, add, and we see that positive 2 is also not a 0 of this expression. So now I'll go back and try again with negative 2. If the negative 2 doesn't work, I'll have to start trying it with fractions, but let's see what happens here. So pull down the 6, multiply, add, multiply, add, multiply, add, and you can see that negative 2 is a 0 of this third power expression, and that means that it's also a 0 of this big expression too. So now this is what we have. Negative 2 is a 0. That means that x plus 2 is a factor, and that means that our function has now been broken down into x minus 1 times x plus 2 times this quotient, so times 6x squared plus x minus 1. And the last two rational zeros are inside this quadratic expression. So we could keep digging through the P over Q list, but all that's left is fractions. So I think instead of continuing to work with the list, now that we have it whittled down to where it's just a quadratic, we can use the factoring skills that we already have to go the rest of the way. So now we're going to say that f of x is x minus 1 times x plus 2 times the two linear factors that make up this trinomial. So let's factor. 6x squared is going to break down into 3x times 2x. And then the signs in our factors need to be different. And last times last has to be 1. So it'll have to be 1 times 1. Now you need to check that outer plus inner adds up to the middle term that you need. And it does. We would have 3x minus 2x, and that does add up to 1x. So now go back and look at the question. It says find all the rational zeros and factor f of x into linear factors. Well, we have actually finished the second part of the question first. Here is f of x factored into linear factors. And now we just have to find the rest of the rational zeros. We found that 1 was a 0 using synthetic division, and we found that negative 2 was also a 0 using synthetic division. And now to find the remaining two zeros, we'll just set each of these factors equal to 0. If 3x minus 1 equals 0, then x is going to have to be 1/3. And if 2x plus 1 equals 0, then x is going to have to be negative 1/2. So there are our 4 zeros for this function. So I do just want to point out to you that in the last example, once we got down to this quadratic expression, we were able to complete the problem by factoring this trinomial. But if this trinomial were not factorable, what we would have to do instead is use the quadratic formula to find the last two zeros. Okay, so now let's have a practice problem that's similar to the last example. Here we have the polynomial function x to the third minus 2x squared minus 13x minus 10. And part A says list all the possible rational zeros. And then part B says find all the rational zeros. And part C says factor f of x into linear factors. So remember, the possible rational zeros are the P over Q list. And remember, the P numbers come from the factors of the constant, so that's going to be 1, 2, 5, and 10. The Q numbers come from the factors of the leading coefficient, so that's just going to be 1. In this case, the leading coefficient is 1, so that's the only factor. All right, now the possible rational zeros are all of the possible P over Q combinations we can make. So you cannot leave your list in this form and say, well, these are my possible rational zeros. You're going to have to say P over Q is 1 over 1, 2 over 1, 5 over 1, 10 over 1, and then each of these could be positive or negative. So we actually have 8 possible rational zeros here. Now part B says find all the rational zeros. So we'll just have to do this by trial and error. Let's start with a positive 1. And we'll do the synthetic division with 1 in the box. Here we have our x to the third coefficient, x squared, x, and constant. Okay, pull down the 1, multiply, add, multiply, add, multiply, add. And we can see that 1 is not a 0 of this function. So discard that, and let's try it now with negative 1 in the box. Pull down, multiply, add, multiply, add, multiply, add. And we see that negative 1 is a 0 of this function. So since negative 1 is a 0, that tells us that x plus 1 is a factor. And so now we have broken our function down into x plus 1 times this quotient. So it's going to be x plus 1 times x squared minus 3x minus 10. Now, the factor that we got from the quotient here, you can see is quadratic. In other words, it's small enough in degree that we can factor it ourselves. We don't need the trial and error process of the synthetic division anymore. So now I'm going to factor this trinomial into two linear binomials. So I'm going to have x plus 1, and then I'm going to factor this trinomial into x times x. The signs need to be different, and 10 has got to be 5 times 2. Let's put the 5 here so that the outer plus inner will add up to the negative 3x that we need for the middle. See, outer times outer and inner times inner, and that adds up to the negative 3x that we want. And so we have completed part C actually, and now we just have to go back and finish part B. We found that negative 1 was a 0 using the synthetic division. Now if this factor equals 0, x would have to be negative 2, so negative 2 is a 0. And if this factor equals 0, x would have to be 5. So 5 is also a 0. And there are our 3 zeros for this function.